Hello, and welcome to this presentation on the OmniXtend RemoteAgent project, or OX Agent for short. This video will give an overview of the OX Agent with a focus on the LeWiz OX Core. For additional information on the OmniXtend endpoint and RISC-V CPU used in this project, please refer to their repositories and documentation. Alright, let's get started. The OmniXtend RemoteAgent project is a RISC-V system-on-chip, SoC, developed to use the Tile Link over Ethernet protocol, also known as OmniXtend, for communication between the processor and a network storage endpoint containing program instructions. The processor used in this project is a combination of the open-source OpenPython framework and the Ariane RISC-V CPU core. The OX core is responsible for translating between the NOC interface on the CPU and the TLOE format for the network interface. The endpoint holds the program to execute and responds to TLOE requests from the OX core. In this more detailed view, we can see the processor is divided up into a core and a chipset. A NOC interface connects this chipset to the OX core. The OX core is composed of a separate transmit and receive path to be described momentarily. The combination of LMAC and PHY is used to transmit TLOE frames from the OX core's TX path and receive incoming frames from the network. As mentioned before, the endpoint contains the program instructions. For debugging and analysis, debug probes are connected to the points shown in the diagram: the connection between the CPU core and chipset, the NOC interface to the OX core, the LMAC FIFO interface, and the CGMI lines to and from the PHY. Now for the key component, the OmniXtend core, or simply OX core. In the OX core's transmit path, the N-to-TL submodule converts NOC commands into Tile Link messages for storage in the intermediate FIFOs. The OX-to-M submodule packages each Tile Link message in a TLOE frame for transmission by the LMAC. The retransmission manager controls retransmission of frames from a local buffer when a negative acknowledgement is received by the RX path. In the OX core's receiving path, the M2OX retrieves received frames from the LMAC and extracts the contained Tile Link messages. The TL-to-M then converts these messages back to NOC format for the CPU. The sequence manager tracks the local and remote sequence numbers to ensure all frames are received in order. For hardware implementation, the combination of OX core, LMAC, and PHY are contained in the OX bridge shown to the right. This OX bridge then integrates with the CPU's chipset in place of the original memory device, as seen to the left. A reset controller manages resetting the bridge's submodules and releases the CPU's reset once the bridge is ready. The complete OmniXtend RemoteAgent design is then implemented on a VCU118 FPGA board. As shown in the previous slide, the CPU and OX core are implemented on the VCU118 development board. This board is connected through a network switch to an Alveo U50 running the endpoint. One of our Linux dev servers is used both for network packet capture and for programming, debugging, and UART serial terminal access for the VCU118. The machine containing the U50 is used for loading data onto the endpoint. For our demonstration, we'll be showing execution of a simple Hello World program stored on the endpoint. First, I'll run the program and show its output on the UART serial terminal. Next, we'll examine the NOC and Tile Link messages from the waveforms captured by the ILAs on the VCU118. Finally, I'll use Wireshark to analyze the captured TLOE frames sent across the network. Okay, so here we are on the dev server connected to the VCU118. We can see that it's programmed with the bitstream containing the complete OX agent system. These three ILAs here are used for the previously mentioned debug probes. The VO allows resetting the OX agent system from this machine. Over here, we have the dev server for the Alveo U50 card. The U50 is programmed with the OmniXtend endpoint from the bitstream indicated down here. The bitstream name indicates the configuration of the endpoint. While we're on this machine, we can configure the endpoint, first by setting its MAC address, making use of the host software provided with the endpoint. If we then print out its configuration and status registers, we'll see the MAC address here, but in decimal. This decimal value does match the given MAC address. Now, the binary program data can be loaded into the endpoint's memory. In this case, it's a simple Hello World program that prints out over the UART serial terminal. The terminal output here shows that the data was written to the memory starting at an offset of 2048 megabytes. This is the address at which the CPU begins execution. Finally, to ensure that the now stale connection used to load the data is not used again, we'll reset the endpoint's connections. Returning to the VCU118, we can now connect to the serial terminal, start a Wireshark capture, and prime the ILAs. Upon releasing the reset to the OX agent system, the CPU will begin execution of the program, printing the output to the terminal, while Wireshark and the ILAs capture the network and system activity. In the terminal output here, we can see that the program has run to completion, printing "Hello World" a total of 32 times. In the Wireshark capture, we can see that the system has entered an idle state as indicated by the periodic heartbeat acknowledgements. On the ILA, we can see the knock commands sent by the CPU and the knock responses from the OX core. Taking a closer look at the ILA capture, we can clearly see the pairing of knock commands and their responses. If we look even closer, we can follow the knock commands through the OX core and onto the network, and then the responses from the endpoint back through the OX core and to the CPU. To see the contents of the TLOE frames on the network, we'll turn to the Wireshark capture. The MAC address ending in 18 belongs to the OX agent system, while FA belongs to the endpoint. At the very beginning, in frames 1 and 2, we can see the OX core's credit advertisements, followed by the endpoint's credit advertisements and acknowledgements in frames 3 through 6. The first GET request from the CPU comes in frame 47, requesting 64 bytes from this address here. The response from the endpoint, in frame 50, contains the first set of program instructions that were stored at that location. This then continues as the program executes, with occasional idle periods, as you can see here. Of particular interest is frame 254, the response containing the "Hello World" string printed to the terminal. We can see in the bottom pane the big endian quad words containing "Hello World, I am heart %d, counting %d of 32. All the way down in frame 17,092, we can see the string "done," which was printed on program completion. The final request and response are in frames 17,186 and 17,188. All frames after this point contain only heartbeat acknowledgements. This concludes the demonstration. The OmniXtend RemoteAgent source code may be found in our GitHub repository. Project documentation is stored in the docs directory. Please begin by referring to this documentation. The OX Core info directory contains the OmniXtend core and test bench along with supporting modules and scripts. Pointing out some of the more important items, we have setup.tcl, a Vivado project setup script. Source this script using Vivado to generate and open the project. The code subdirectory. This contains all source and simulation code and scripts. Code is further divided into constraints, IPs, simulation source, and design source. Both simulation and design sources are broken into categories by major component, such as the OX Core and LMAC. The FPGA directory contains FPGA-specific implementations and supporting scripts, resources, and examples. The VCU118 directory contains all files related to the OmniXtend RemoteAgent CPU for implementation on a VCU118 FPGA board. OX Agent links to our fork of the OpenPython repository, containing the OX Agent core, LMAC, and other critical components of the OX Agent system. Example contains the OX Agent bitstream used in the preceding demonstration, along with the corresponding ILA and Wireshark captures. Scripts contains a basic byte flip script useful for converting compiled program instructions endianness for compatibility with the endpoint. The U50 directory contains files related to the OmniXtend endpoint for implementation on an Alveo U50 accelerator card. This currently contains the demonstrated "Hello World" binary and a link to the main OmniXtend endpoint repository. Thank you for your interest in our OmniXtend RemoteAgent system.